Okay, we're short a few people, and it's a little bit early, but I wanted to show this one slide. We'll get going with the lecture in a few moments, but this is a slide I forgot to talk about last lecture when we were talking about transformations. I showed you this slide, which was the organic matter slide, organic matter transformation. This is basically just different temperatures, decomposition. But this is actually mineralogy, and we're going to talk about some of this today, but we'll talk about more of this later on. But I wanted you to sort of see this schematic here and these pictures that are associated with the schematic. Basically what we're looking at is we're looking at different secondary minerals. Now, do you guys remember what I meant when I talked about secondary minerals? These are minerals that are formed at the surface of the planet, sort of in situ type of situations. But they're secondary, i.e. because they've taken a primary mineral and they've been weathered and modified into something else, into another mineral. So they're a secondary mineral. Now, I put this slide up here not just for you to see that we have secondary minerals, but I wanted you to see that there's a whole sequence to these secondary minerals, and there's conditions, both what the primary mineral was as to what it's producing, but also there's conditions, climatic, weathering rates, and things like that, that produce a variety of these secondary minerals. The example, the take-home message from last lecture was that these were all transformations. These are examples of transformations. Today, we're going to be talking about this basically the same slide in a couple examples. But this is going to be these are examples of weathering producing something else. Okay, the weathering from a primary is producing a secondary. The weathering from a secondary is producing another secondary. And we're just looking at that whole sequence. Does that make sense to everybody? And I apologize I've totally spaced on this slide. But all right. Any questions? Everybody survived the break? I think we're almost all here. I think we're short like 4 or 5 people. Everybody survived the break? Yes, yes, you guys. I hope you guys got off campus. Anybody get to the farmer's market? One person got, oh, so more than one person got off campus. First time farmer's market, or you've been there before? So it was pretty cool, huh? Crazy people down there. But so anybody leave campus totally? Leave Tompkins County? Good chunk? I'm sorry. No. I got one thing I wanted to talk about before we started getting into the lecture. Most of you guys have been noticing that the video, I keep forgetting to talk about this, but the video in the back, you know, the guy behind the curtain type of thing. A couple of questions have been about when you guys will be able to see them. One was the availability of the video, so that you guys can start bailing class, in essence. No. The people that are going to be doing the editing are supposed to be back this week. I'm not sure. And then we're going to start editing it. The hope is that the lectures will be online prior to the first prelim. Okay, but that's just because I said that doesn't mean it's a guarantee, but that's the hope, okay? I will tell you when they're online. All right? Cool? Beans-ish? All right. So let's get started. We've gone through the soil forming factors, and we've gone through the soil forming processes. So in essence, we have some sort of context as to how these soils are coming to be. Okay? I wanted to talk a little bit about, okay, once we get to that point, sort of some of the questions are, well, if we're going to talk about these factors and these processes, we have to have an idea of what these factors and processes actually are. And so we're going to start going into more detail. Okay? And I start with this slide. I stole this from the web someplace. I'm not really sure where. Otherwise, I would have given it credit. But basically, this, if you think about parent material, where is the ultimate source of this parent material? Well, it's crustal material. It's coming from the planet. Yeah, I know Sagan used to say we're all children of stars. We're all made of stardust. Is this out of? I know it's totally out of context. Sorry, but does that sound somewhat familiar? Okay, all right, all right. Well, here's that stardust, and this is the stardust that makes up our planet. Okay, and this is basically a pie chart showing the abundance of these different elements in our planet, or on, in, around our planet. Okay, you'll notice that oxygen is the big one. Okay. Goes to silicon, aluminum, iron, calcium, sodium, potassium, and then a whole slew of other little ones that are not, I mean, the pie chart is so small it's not even there. Okay, that sliver. Okay, so this is what most of the minerals are made out of. And they are made predominantly out of these 3. Now, I'm going to be talking about weathering today, so I'm basically going to be talking about how things break apart. But let's sort of take a look at this slide right here and turn it around. They're going to talk about it going this way, but I want to talk about it going this way, because the rest of the lecture we're going to be talking about it going this way. All right? So we start with these basic elements. These basic elements form together. Okay, here's an oxygen and a silicon, basically creating a silica tetrahedral. Okay, these silica tetrahedrals, basic chemistry. These elements are basically sticking together. Okay, they form larger units, and this is a quartz crystal. That quartz crystal is the particle within a grain of sand. Sand is basically quartz. Okay, the sand comes from sandstone. Okay, in this case, the individual grains of sand are compressed and turned into a sandstone, and the sandstone basically becomes exposed. Okay, so the way they're telling the story is this way, breaking it down. This is how it's built, and then the rest of the lecture is basically we're going to talk about how it comes apart and how it ends up where it is. Does that make sense? Pretty simple schematic. Just sort of keep this in mind. Now, first of the 5 soil forming factors, parent material. What is parent material? Well, soils are basically a stage in a geologic cycle. Okay, and let's talk about that geologic cycle, because the soils are basically formed at the surfaces due to surficial processes. But how does that material get there? And let's start here with magma. Okay, magma sitting underneath the crusts, liquid rock in essence, hot, flowing. Okay, this material potentially can move up from the core, move up towards the surfaces of the planet. Okay, as it moves up, it's going to potentially cool, and as it cools, it's going to start solidifying. This can be uplifted and ultimately exposed, and because the material basically came directly from the magma, we call it igneous rock, and I'll explain what this is in a moment. Okay, this igneous rock is now exposed, which then means it is exposed to surficial processes. The climate, wind, all the things that are dynamic up here at the surface of the planet. This material then becomes the parent material for soil. A lot of stuff happens here, but ultimately, all the stuff that happens here will be subducted, put back down into the magma, and turn into magma again. Okay? Just the cycle. It's geologic cycle. A lot of you guys have probably seen it something more like this, but basically that cycle is this blue line. Here's our magma. It's turning into igneous rock, partial melting of metamorphics, but this material gets uplifted and cools, turns to igneous material that's exposed. Surficial processes, weathering, transportation, deposition, moves it down. It can then be turned into sedimentary rock, which we haven't talked about yet, or it could be that sedimentary rock could be heated up and it could be turned into metamorphic rock, but ultimately that stuff is going to go back down into the lava, the magma, and turn into this liquid rock again. Does that make sense? Now, the cool thing about this is the minerals that come out are dependent upon what elements are in this magma soup. Think of these elements as ingredients in a cake. Depending upon how much oxygen or any of these other elements I have, and how I cook it, how hot it is, how quickly it takes to expose to the surface, I am going to get a variety of different minerals. Does that make sense? These elements are going to be put together in a variety of different ways, and they're going to produce a variety of different minerals. Okay? All right. These minerals are going to come up to the surface, and depending upon how these minerals are put together, they're going to weather, transport, and be deposited in different fashions, producing different materials on the surface, hence secondary minerals. Does this make sense? So, yes, thank you for that voice. So hence, we basically have 3 different types of rocks that are made up of these minerals. which the minerals are ultimately made up of these elements. Okay? The first is igneous. There are two types of igneous rock, but igneous rock is basically the material that cools from this magma and turns into a mineral, and it becomes a rock. There are two kinds. There's extrusive and intrusive. Extrusive is magma that's cooled at the surface, like a lava flow. It cools very quickly. Okay? As a result of this cool environment and this fast cooling, or solidification might be a better way of saying it, it produces small crystals. We also have intrusive magma, which cools below the surface. It cools very, very slowly. And if it cools slowly, even though I have the same ingredients, I'm going to produce different types of things. Okay? This magma cools below the surface, and it produces large crystals with differential or different rates of crystallization per mineral type. This is when you start getting these really large crystals. Okay? Now, remember me talking about the ingredients. We have two different types of ingredient pools. And the reality is there's lots, but they basically break up into two different groups. One is the sialic, silica aluminum, sialic. They contains mostly, these minerals basically contain mostly quartz and potassium feldspars. Okay? They are resistant to chemical weathering. We also have the mafic, iron, magnesium-rich materials. They contain less quartz but more magnesium and iron-rich minerals, and they are not very resistant to chemical weathering. So right there, you have a clue. Okay? I've got extrusive stuff, small crystals. If these small crystals happen to be mafic, I've got small crystals, means lots of surface area, and they're very easily weathered. I'm going to have soils forming really quickly. On the other hand, if they're intrusive materials and they happen to be sialic, large surface areas, large crystals, small surface area per volume, and they're resistant to chemical weathering, soil formation is going to be a lot slower. Does that make sense? Okay, so those are the igneous. Igneous materials, you start with these primary rocks. Okay? Surface stuff happens. Okay? If this igneous material, the secondary minerals and the products of this weathering of this igneous material gets buried, it potentially can have an overburden that is so heavy that the stuff gets compressed. It can get pushed together. Okay? And that stuff basically creates a hard rock as well. It's a rock that's formed from compression, and we call it sedimentary rock. Okay? I've got a series of materials here. These are the primary materials from which the sedimentary rock is formed. I've got piles of this stuff. It gets buried. If it gets buried and compressed and turned into a rock, this is what it turns into. If it's a gravel, it gets turned into a conglomerate. Something that looks like this. I'll have a better slide of this in a second. Okay? If it's sandy material, sand grains, compressed, it turns into a sandstone. Something that looks like this. That looks like a sand grain, but it's the same color as sand. It's just basically particles of sand pushed together. Okay? If I have silt or clay, silt will turn into a siltstone. Clay will turn into a shale. Do these terms sound somewhat familiar to you guys? Okay? If that's what I get these layered, very soft rocks. Okay? If I have carboniferous, this is a word I cannot say, carboniferous rich shells, sea organisms and things like that. These materials, these animals die, they build up, they get buried. We start compressing them, and they basically turn into limestone. This is a good example of a conglomerate. You can actually see the gravel. This is not cement. This is gravel that's been compressed with smaller materials. It's basically pushed together, mixed, very mixed mineralogy, but one type of rock. A conglomerate of lots of different types of rocks. Pushed together, held in place. Okay. Now, we have a third type of stone or rock. Okay, we call it a metamorphic. And basically a metamorphic is a sedimentary rock that has been heated up, but not completely melted. It's been heated up enough that chemical reactions occur to it and potentially bind it together. Okay? If I have a limestone, that's that calcareous material, If I have a limestone, it's a sedimentary rock, and that limestone has been melted and heated up, it can turn into a marble. The shale can turn into a slate. The granite can turn into a gneiss. The sandstone can turn into quartzite. Okay? They are formed under intense heat and pressure. Hence the sentence there. Okay, questions on this one? Go.
Metamorphic will become sedimentary rocks.
Well, igneous is already it's been formed under heat, so it's already in its heated stage. But I mean, here's a good, the sand itself was formed, so the quartzite was formed in igneous. So the sand grains themselves are in fact igneous. The sandstone is the sedimentary, and the quartzite is so that's sort of a sequence of it. That sort of makes sense? Does that make sense to everybody? Yeah? Okay. So let's move on. Depending upon how hard or how consolidated these materials are, it's going to affect the superficial process, the effect of that. So it's going to affect the weathering rates. So if I have a really hard rock, I'm going to have slow weathering. Hence, soft rock going to fast weathering. And if the material is totally unconsolidated, it's going to be very fast. Okay? A lot of this has to do with the fact that basically the smaller the particles are, the less connected they are, the more surface area per volume I'm going to have. The more surface area per volume I have, the more surface area I have for weathering to occur. If I have a rock that's this big, the weathering is going to occur on the outside. On the other hand, if I have a rock this big, and it's actually grains of sand, the weathering is going to happen throughout. And if it happened to be a soft material, it's going to be even faster. If it's not sand, it's shale, pieces of shale. Does that make sense? So that, in essence, basically tells us what this parent material is. And so let's break that parent material up into sort of its effect on the product of weathering. Okay? So the mineralogy is definitely going to influence the secondary mineral formation. You saw that slide in the very beginning, right? Okay? But depending upon what the ingredients are in it, as it weathers, it's going to affect soil fertility. If I have a parent material that the mineralogy in it, or I should say the elements in it, are not minerals, are not aluminum. Let's say, imagine it's aluminum. It's not a nutrient. Okay? It's a poor nutrient material. As it weathers, it's not going to produce nutrients. On the other hand, if I have a basalt type of material, okay, a basic igneous rock, it's got a lot of different varieties of elements in it. A lot of these are nutrients. Okay? As that rock weathers, these nutrients are going to be released, and the soils that are produced from this basalt parent material are going to have good fertility. Does that make sense? And this also goes back to particle size, which I've already sort of talked about. So I don't think you need to see that slide again. All right. So we've talked about these parent materials. We've talked about the rock types and the sort of sequence of weathering and the superficial processes. Let's actually talk about what those superficial processes are. And we're going to talk basically about the weathering process themselves. We have two types. We have physical weathering, where you're actually banging things together. And we also have chemical weathering. Let's start with the physical weathering. Okay? There's basically 5 different types of physical weathering. Okay? We got freezing and thawing. You can imagine something expands and contracts. When it freezes and thaws, things are going to break. Okay? We also have uneven heating. Okay? If I have a big rock and one side I heat and one side stays cold, you can imagine that the hot side is going to expand and the cold side is not. And I'm going to have differential sizes, which will potentially create cracks and fractures. Okay? Next one is abrasion. I'm literally taking a sandpaper to it. Okay? This can be an ice, this could be water, or it could be wind. Next one is shrinking and swelling. Okay? As things get wet and dry, wet and dry, wet and dry. Okay? And then finally, biological stuff, roots themselves. If I have a crack, okay, yes, it probably started from something else first, but I got a crack, a root gets down there, that plant is going to start growing, and that root's going to start expanding. And if it starts expanding, it's going to expand that crack, and the thing's going to break. Does that make sense? Okay, so let's give you some examples. Guys, see this slide? It's visible, pretty visible. Okay, stream, rather large boulders here. Okay, the boulders are rounded, which is an indication of what? Water tumbling. Okay, if something's rounded, it's been tumbled. Okay, so these boulders, rather large, that tells you that this stream, at some time, if not all the time, every sort of flood, but if not later, or I should say, at some time, this stream has produced a lot of water, because you need a lot of water to move those types of boulders. Okay, but as these boulders are moving in the water, they're tumbling, they're smacking up against each other, they're grinding stuff away. You can see these boulders are basically sitting in the product of their grinding away. Okay, this is basically sand with sandstone boulders. Here's another water feature. I have a crack forming, so for whatever reason, water gets down here, it freezes, it expands, it breaks. Okay, produces very distinct scree fields. Has anybody seen these scree fields? Okay, but you're basically looking the angle of repose with these rocks basically from summit all the way down. Okay. Another good example. Okay, this is expansion. Okay, as rocks get exposed, imagine how big this rock is. I mean, this is a mountain-sized rock. Okay, so as it comes up and it's exposed to the surface, what's going to happen to it? Well, as it's exposed to the surface, the stuff that's up here doesn't have an overburden on it anymore. The pressure is released. So as a result, I mean, if I have something compressing and then I'm releasing the pressure, you can imagine that the stuff at the edges, at the place that the pressure is being released, is going to expand. Okay, and the stuff below it still has pressure on it, so it's not going to expand. And if I have the edges expanding, I'm going to start seeing fractures. Okay, you can start seeing these fractures. Now, that's not to say once I have these fractures, other processes like water is going to get in there. But the initial fracturing is due to this release. Okay, I mean, this is a mountain-sized boulder. It's a big rock. You can imagine that the bottom of this rock has got a lot more pressure than the top of the rock. And when it's exposed, you're going to relieve pressure at one point, differential pressure release, and you're going to have fractures. How about something a little bit smaller? Do you see this sort of flaking here? This is heating. The sun is literally shining on it. It's heating up the very surface, the skin. Okay? If it's heating things up, it's going to expand. It's not going to be like this where it's going in very deep. Okay? It's very much at the surface. Okay? It heats up and it basically potato chips. It flakes off. Has anybody seen something like that? Oh, I should go back to this one. Has anybody seen something like this? We have it a lot around here. We have a lot of this around here as well. It's just you need to find the exposed points. This is an older landscape from a geologic sense. From a geomorphic sense, it's very young because of glaciation. So let's move on. These are my favorite slides from this lecture. But I mean, you can see this crack right here. I mean, the plant's roots have basically gone down that. And here, I mean, this is basically an Ansel Adams shot. I mean, that tree has basically filled that and it's expanding it. That's a cool shot. I have no idea where I got that one either. But this is physical weathering. The thing is literally being ripped apart. All right. You made it through that one? Let's move on to chemical weathering. There's basically 4 types of chemical weathering. We're going to talk a lot about this later in the semester. So I just wanted to sort of touch on this right now. You have hydrolysis, which is basically an addition of a proton to the structure. This is at the chemical level. I'm taking a proton, I'm adding that proton to the chemical, to the element or the mineral. Okay? I can also have hydration, where instead of a proton, I'm literally adding a water molecule. Okay? I also have oxidation and reduction processes, and we'll talk about this when we start talking about colors. But basically, I'm seeing a gain or loss of an electron. You guys see the trend here. I'm going through proton, I got water, hydrogen, proton, water molecule, electron, or I can basically have a dissolution carbonation reaction where the molecule is literally dissolving. Okay? In this case, we're looking at carbonic proton from carbonic acid. This proton reacts, and basically it's an acid. This is my weak acid in a million years story. Okay? I take that acid and I'm basically just totally weathering something. I'm dissolving it. Okay? One example, this is a hydrolysis example, but basically I'm looking at a potassium aluminum silicate here. This is the mineral that I start with. My water molecule right here, water dissociates. That's the term for pH, but it dissociates into a proton and a hydroxide. In this case, this proton is going to react with this mineral, and it's basically going to react with that potassium. The proton switches into the potassium's location. The potassium is now in solution, where it can become an element for nutrition, or it can be leached from the system. This is fertility. Okay? But the molecule, the element that we started with, this is now something different. It's been chemically weathered. Okay? Weathering doesn't necessarily mean destruction. It could, in fact, be a building up, but we're looking at the destruction of the initial material. Does that make sense to everybody? Down the bottom is basically the balanced equation, but this is the slide that I started today's lecture with. Here's those primary minerals. Some sort of chemical reaction producing these secondary minerals. In this case, I start with a primary mineral up here, I lose the potassium, and I end up with an illite. Okay? Start in here, if I lose a magnesium and I lose a potassium and I gain a water, I'm moving into the vermiculites. Down here, if I'm in the mafic end of the spectrum and I lose a potassium, I'm moving into the clay chlorites. Remember, these primary minerals, these minerals down here are different than those minerals. So even though I'm losing a potassium in both of these cases, I'm producing different secondary minerals. Ultimately, I'm going to have enough weathering of potassium or gain of potassium or loss of magnesium or gain of magnesium that I'm going to move into the smectites, the montmorillonites. If I start losing silica, I'm going to start moving into the kaolinites. And if I lose even more silica, I'm basically into the iron and aluminum oxides. Okay? We feel comfortable with this? We will revisit this one. I don't expect you guys to memorize this. Okay? Which brings us right back. Oh, go. Question.
The mafic rocks are more chemically reactive. Is that what you said?
The mafic rocks are more chemically reactive. They're sort of at this end of the spectrum, but that's just, having said that, I mean, this stuff is, it is reactive. This just happens to be more reactive. This takes a lot longer than this. Which brings us right back to this slide. Now, does this slide make a little bit more sense? We start with the magma. We have uplifting and igneous rocks. Superficial processes produce sediment. Okay, that sediment or that igneous rock, that sediment material can become soil, but that sediment also can be transported and it can be buried. Okay, in that burial process, if it gets buried deep enough, it can actually be turned into hard rock and becomes a sedimentary rock, which in turn can be weathered. Okay, this material can be subducted, put back down, and it can be heated up. And for whatever reason, if it doesn't go back down to the magma but actually comes back up to the surface, we have this metamorphic material, which in turn can be weathered, produce different soils, but ultimately all of this stuff will get back down into the magma and we'll start the cycle again. Cool? Questions? Do we feel comfortable with this? Okay, so we've talked about these parent materials. We've talked about the geologic cycle. We haven't talked a lot about, we've talked about the chemical and physical weathering, but we've talked about the transformation end of this, but we actually haven't talked about the transportation end of this. So let's spend a little bit of time talking about how these things get moved, because the movement of these materials is also part of the weathering. I mean, certainly if I start talking about water, well, water is weathering, but it's also moving material. Wind is weathering, but it's also moving material. Gravity happens. Okay, so here's that diagram down here. And basically what we're going to look at is this is a schematic of how these materials move and the portions that are turned into soil and sort of the flow chart of it. Okay, so let's start right here with exposed igneous rock. We've come up and we're now exposed. At this point, I could have weathering. And if I have weathering and surface formation, I can produce soils. Now, this material can also be exposed to heat and pressure and basically be turned into a metamorphic rock. Back to the question that you brought up. Okay? This can be weathered, and superficial processes happen, soil formation happens, and we can have a soil there as well. Okay? If it is superficially weathered, this material can be weathered and transported, and it can become unconsolidated material. Okay, it can be turned into sedimentary rock, but this material, through weathering and soil formation, can become soil, and in turn can go back to be unconsolidated material. Does that make sense to everybody? This material can be buried, cemented. This basically comes as cemented rock, sedimentary rock. It can be uplifted, and it can become exposed sedimentary material. This is unconsolidated material. This is the stuff that was weathered away from here. Okay? This sedimentary, exposed, weathering and surface or soil formation can produce soils. If this goes under heat and pressure, it can become a metamorphic rock, and the cycle continues. Ultimately, doesn't matter where you are on this chart, ultimately, you're going to be subducted again, turn back into magma, and the cycle will start again with exposed igneous rock. Now, this is a geologic cycle, lot longer than a soil cycle, which is a lot longer than a biological cycle. Okay? Good handle on this? Because I want to talk about we've been talking about the soil formation, we've been talking about the minerals, but I want to start talking about the transport. Sediment transport. How does this stuff move around? Okay, and there's a number of different agents of transportation. The first one we're basically going to talk about is wind. Okay, I have introduced you to this because I've talked about loess. That very first soil pit that we went to. Periglacial environment. The glaciers recede enough that the lake's levels drop. What happens? We have this cold body up there. We got this warm body down there. We create lots of convection currents, lots of winds. That wind selectively picks up the silt and redeposits it. An aeolian deposit. Make sense? Loess. Okay? You can have aeolian silts. So this is the loess, but you can also have aeolian sands. Okay? The sand doesn't actually get picked up. It gets saltated, but basically what you're looking at is you're looking at sand dunes, where I'm looking at blowing material. It's not going high, it's just being blown. Okay? Sand hills of Nebraska, any beach dune that you think of, the Sahara, these big, huge sort of sandy areas. Okay? Does that make sense to everybody? Loess has excellent sorting. Why? Do you guys remember the whole story about why it's selectively picking up the silt over everything else? Right? Why is it? It's selectively picking up silt because it's not large and it's aerodynamic, and unlike clay, it doesn't stick together. So it acts as an individual particle. Now, the important thing here is when you think about this loess material, you say excellent sorting. Well, we always think of, well, it's sorting the dust. It's putting the silt on top. But at the same time, it's also sorting out the parent material from which it came, because it's selectively picking the silt out, which means everything else is being left behind. Sorting. Okay? Vertical uniform particle size is coming down as large components. The wind is uniform energy. You're getting large vertical depths. Okay? And it's also deep rapid weathering, because if I have small particles, a lot of surface area exposed, it's going to weather very quickly. Now, you saw that on the Arkport soils. What happened to that loess material? It weathered quickly, turned into clay, and where did that clay go? That's where we got the clay bands. Those soils, parent material-wise, there is no clay there at all. Sand down below, silt. Yet we find bands of clay in it. It's because we're looking at the weathered silt moving down. Okay, wind is pretty powerful stuff. This is basically sandblasted. The sand, the particles in the air is doing the grinding. The wind itself isn't doing the grinding, but the wind is the carrier for that sand, basically driving through. Okay, now it's interesting to take a look at this feature, because one would think if I got sandblasting, I'd have it all throughout the whole thing. But the reality is we've got to go back to this sorting equation. There's vertical partitioning here. The wind is only picking up the sand so far. It's not like it's picking silt up and carrying it, miles. You heard me tell you that the Caribbean and basically the southeast of the United States is being fertilized by dust from Africa. It's not sand that's coming across, though. And this is a perfect example. Where's that sand weathering the stuff away? Down here. If it was high, it would be weathering this whole thing. You'd have a column. Does that make sense? Yes? Questions? Go. Well, all the particles that are in that wind. The wind itself, if there's nothing in the wind, it's not going to have as much power. Yeah, it could get inside stuff and sort of rip it off. But if that wind is carrying something, it's going to be hitting, whatever it's carrying is going to be coming in here and pelting this. Does that make sense? So it's like sandblasting, literally, where you have pressurized air, you put sand in, and you shoot something, and you basically peel off the paint. Okay, it's the same thing happening here. The wind is strong, but it's not strong enough to carry the sand all the way up here. It's basically concentrating it right in here. Does that make sense? Questions? We also have ice. Let's say glaciation advancing across the north of the United States and Europe. But basically this material pushes through and it grinds stuff up, but it also carries stuff with it. Okay? Because of its process, this material is basically unsorted. It's everything. Everything from huge, gigantic boulders all the way down to clay-sized stuff. Because it's not just transporting it. As it's transporting it, things are being ground up more. So even if I started as a boulder way up in Canada, potentially by the time it made it down here, it's not going to be a boulder anymore. It's going to be clay-sized stuff. And so as a result, you get this unsorted, loose mixture of everything. Particles from clay to boulder size. So we're talking about ice transportation, okay? And we're basically looking at this unsorted, loose mix of basically everything, okay? Of all different kinds of sizes, shapes, colors, materials, mineral types, everything, okay? The interesting thing about this is they get classically deposited in very classic forms. And these examples of the till plain moraines, came kettles, eskers, all of these, they're very distinct in their formation, okay, when they're laid, okay? Some ice distribution. This is, you got a lot of boulders, you got some rounded. So this was actually, there was some water distribution in here, but you're looking at a complete mix of materials, fines all the way up to large, okay? Another example is potentially this. I don't know, can you guys see this? It's an old picture, but we're looking at rock debris that was basically directly from the glacier melting ice. It just basically came off, and you can just sort of see, it's just this really thick mix of everything. Go.
For that last picture, is it even considered a soil, or is that still?
Well, there's definitely soil formation going on. You can see the enrichment at the surface. But how many years has this been going on? I mean, if it's all sand and rocks, there's not a lot of stuff. It's pretty resistant to chemical weathering, but you certainly can see, I mean, there's some fairly large trees at the top. I don't have a scale there, but that's maybe 50-year-old trees.
But if you were to take like a monolith of that, or if you were to make one, like would it have distinct horizons after that?
Went down in here. No, this is all paramaterial. This is all sea. It would be all up there. I mean, go take a look at like the Otisville or something like that out there. It's basically the same type of, now that's more stream rounded, but it's the same type of material. The same is happening here. I don't know if you guys can see the very top. It's kind of a tough picture to look at. But you can see that it's a little bit darker at the top. Now this has been a cut. This is a cut, but see if I get another one. No, I know that's the only two I have. But take a look at some of those monoliths out there. It's all going to be at the surface, but down here, there's not a lot of differentiation happening. This is still paramedic. This is sea material. Okay. We also have water transportation. Water is transporting as well as weathering, just as the ice and the wind is. Okay. We have glacial outwash. These are water deposits that are basically coming from this melting glacier. This is a sort of a pseudo. This is not necessarily till, but this is, we call it till. This is a mix of water drop stuff, ice drop stuff, just basically dropped. Okay. We have lacustrine. This is clays, the lake Glade stuff. And then we have alluvial stuff, which is the streams, floods, moving things. Okay, here's some examples. These are more water erosion and depositions, but you're looking at the water cutting into that, water cutting into this and moving things farther downstream. And this is the downstream. You can sort of see these strata. I don't know if you see these sort of lines. You can sort of see it moving up. Here's another one. But basically, you're looking at the sands and materials basically laid on top of it. This is pretty deep. I mean, there's a person. You can see the soil forming at the surface up here. And these darker horizons way up at the top. This is all that water deposited materials. I threw this in here because this looks like it's rock. But this is actually what we call, this is lake laid material. And this is actually very large varving, V-A-R-V-I-N-G. I think it's I-N-G. And basically what's happening here is you're looking at seasons. Wintertime, the lakes freeze over. Okay. Summertime, they're open, which means wind can move across the water. Now, if wind moves across the water, it may not be a lot of energy, but it's enough energy that it creates some turbulence in the water, and it keeps the finer particles in suspension. Wintertime happens and it ices over. That wind isn't there anymore. Okay? Water isn't flowing into the lakes anymore. The water column gets calmer and finer particles come out of suspension. Does that make sense? And so as a result, you have a stratigraphy of coarse to fine, coarse to fine, coarse to fine. And you can actually see the layers. Okay, it's called varving. And when we get up to, I think about 3 weeks, 4 weeks, I'm hoping to dig a borehole down and we can pull this stuff up. It comes up, this is really big stuff. I mean, you can see the size of the leaf. This is thick stuff. But the stuff that we find around here, fairly thin, and it comes up like a very platey texture, a platey structure. Because what's happening is the clays that settled in the wintertime are forming chips, and the sand that was there being laid in the summertime is basically the breakpoints. And so you can take this and it looks like it's just chips. It's pretty interesting stuff. Then we also have gravity. Okay, gravity happens. It carries materials short distance down slopes, basically erosion. This gravity transported material we call colluvium, and here's sort of a concept slide of it. Material that's up here, gravity pulls down and creates this material, this deposit right here. This angle here is called the angle of repose. It's basically the angle that the material can hold its bearing strength on. Okay, Buffalo Street. Now, if Buffalo Street, guys, everybody know what Buffalo Street, that really steep street that goes straight down to the Commons or just to the south, just to the north of Commons, extremely steep. That is a stream delta. It was a stream delta that was formed underwater, so its angle of repose is a lot steeper. If that same stream was depositing stuff above water, not in the lake, that stream delta would not be formed like this. That stream delta would be formed like this. Right? Does that make sense? Okay. Gravity depositions, you're basically looking at this colluvial material just sliding down slope. I think I have one more slide. Nope, that's it. Okay. Sorry to abbreviate it. There's actually a lot more stuff I would have talked about in there. If you have any questions about any of this, come talk to me because I know we got shortened our class today. Okay, otherwise, be free. Go. Have a great day, guys.